Friends, in the last class I have introduced the concept of random variables. We have seen that the random variable can take values which are finite in nature like 1, 2, 3 etc., or they can be countably infinite like we can say 1, 2, 3 and so on, or they can take values over an interval, for example height, weights, price etc. So, we accordingly distinguish them as discrete or continuous random variables. I have elaborated upon discrete random variables and how to describe the probability distribution of that. Based on the probability distribution, we look at the concept of the mean or the expectation or the expected value of a random variable and the variability. Variability is measured in terms of variance of a random variable which I defined. Let me further explore it little bit. So, let us consider we can consider alternative formula for evaluation of the variance. So, let us consider what formula I wrote. So, I wrote variance of x is equal to expectation of x minus mu square, where mu itself denotes the mean of x or the expectation of x. Let us expand it. So, this is equal to expectation of x square minus 2 mu times expectation x plus mu square. Now, here I will try to use some properties of the expectation. So, let me call it 1. To simplify 1, we will use some properties of expectation. The first property is that expectation of a constant is constant. Okay. This is simple to see because expectation of C, you can say the value multiplied by the probability. So, here whatever be the value of random variable x, it is actually, so P1, P2 and so on, Pn say. Suppose the random variable is taking these probabilities. So, it becomes C P1 plus P2 plus Pn, that is equal to C into 1, that is equal to C. So, expectation of a constant is the same constant. Similarly, if I consider random variable x and I consider a linear function of that, then it is equal to a times expectation of x plus b. So, this is also very easy to see. If I write expectation of ax plus b, then it is equal to ax1 plus b into p1 plus ax2 plus b into p2 plus and so on axn plus b into pn. So, this you can expand a times x1 p1 plus x2 p2 and so on plus xn pn, that is this term, plus b times p1 plus p2 plus pn. So, this is nothing but expectation of x. So, you get a times expectation of x plus b times p1 plus p2 plus pn is 1. So, this means that expectation is a linear function. Okay. So, if we use this property in this expression, then we will get, so using these properties in one, we get variance of x is equal to, so this is expectation of x square, so this will go inside expectation of x square minus 2 mu times expectation of x plus expectation of mu square, which is mu square, because mu square is a constant. So this expectation of x minus mu square has now become this value. So we can write it as expectation of x square minus 2 mu, and what is expectation x? That is mu. So it becomes 2 mu square plus mu square, that is equal to expectation of x square minus mu square. So this is an alternative formula for calculation of the variance x. That means we can say variance of x is equal to expectation of x square minus expectation of x whole square. This formula is sometimes very useful in calculation of the expectations, because given a random variable, it is easier to calculate expectation x and expectation of x square, because this is direct one, whereas in the last one you have seen that expectation of x minus mu square, if you calculate the number of terms to evaluate, you have to consider a lot of differences and their squares, etc. So let me use this and calculate variance in one of the earlier problems. So let us consider that score of the card problem. So let me show that example once again, and we are having the value here score of the card problem had the distribution probability x equal to I is equal to 1 by 13 for I is equal to 2 to 10, probability x equal to 15 is 3 by 13, and probability x equal to 18 is 1 by 13. We had already calculated expectation of x, that was equal to 9. Now for the same one, if I calculate what is expectation of x square, so expectation of x square will become sigma I square 1 by 13, I is equal to 2 to 10 plus 15 square into 3 by 13 plus 18 square into 1 by 13. You can actually try to compare it with the expression for expectation x. So whatever value x is there in expectation x square, we are putting x square, and pi's are the same. So this is the easy way of looking at the calculations. Now in order to evaluate this, we apply the formula for the sum of squares of first n integers. So first n integers, you had the formula n into n plus 1 into 2n plus 1 by 6. From that sum, the first term is removed, because here it is from 2 to 10, so I is equal to 1 is not there. So this becomes then, you can actually look at the calculation, 10 into 11 into 21 by 6 minus 1, and 1 by 13 let me keep outside, plus 225 by 13 into 3 by 13 plus 324 by 13. So one can easily simplify all these terms, it becomes 1383 by 13. So now variance of x is equal to expectation of x square minus expectation of x whole square, that is 1383 by 13, and expectation x was 9 here. So we look at this 9 square. So after certain simplification, it is equal to 330 by 13. Now you can see that this variance term, it is actually giving you the squared deviation from the mean. So one reasonable measure to bring it to unit of measurement, because now it is squared units of measurement. So, if we take square root of that, that gives you the variability in terms of the same units of measurement. For example, if you are looking at centimeters, you are looking at kilograms, or if you are looking at liters, then the units must be same for description. So, we consider the standard deviation. So, we define standard deviation of a random variable x is defined. So, we write S d of x is defined to be square root of variance of x. So, let me look at some more problems here. Two distinct fair dice are rolled once. Let x denote the absolute difference of the numbers shown on the upper faces of the two dice. So, we want to find out the distribution of x and say what is variance of x. When the two dice are rolled, the number of possibilities are 36. You are having the sample space 1 1, 1 2, 2 1, 2 2, 2 6, 3 1 3 2, 3 6 and so on, 6 1 6 2, 6 6. So, if we want to look at the definition of the random variable x, it is the difference. If we have 1 1, the difference is 0. If it is 2 2, the difference is 0. If it is 1 2, then the difference is minus 1 and absolute difference will become 1. If it is 3 6, then the difference is minus 3 and the absolute difference becomes 3 and so on. So, the possible values of x, that is absolute difference, they are 0, 1, 2, 3, 4 and 5. So, you can say the absolute difference is 0 for 1 1, 2 2, 3 3, 4 4, 5 5 and 6 6. There are total 6 cases. So, what is the probability that x equal to 0? It becomes 6 by 36, that is 1 by 6. Now, the absolute difference 1. What are the possible cases? You can have 1 2 and then of course 2 1, then you can have 2 3, 3 2, 3 4, 4 3, 4 5, 5 4, 5 6 and 6 5. Total number of cases is 10 cases. So, what is the probability of x equal to 1? that becomes 10 by 36. You can also simplify it by writing 5 by 18. Now let us look at the absolute difference 2. One 3, 3 1, 2 4, 4 2, 3 5, 5 3, 4 6, 6 4. So you have total 8 cases. So probability that x equal to 2, that will become 8 by 36, that is equal to 2 by 9. Now let us look at the absolute difference 3. One 4 4 1, 2 5 5 2, 3 6 6 3. So you have total 6 cases. So the probability that x equal to 3, that will become 6 by 36, that is 1 by 6. Now the absolute difference is 4 for 1 5 5 1, 2 6 6 2. There are total 4 cases. So the probability that x equal to 4, that will become 4 by 36, that is 1 by 9. Similarly, let us look at the absolute difference 5. One 6 and 6 1, that is total 2 cases only. So the probability of x equal to 5 is equal to 2 by 36, that is equal to 1 by 18. You can cross check that it is a valid probability distribution. The total probability is 6 plus 10 16 plus 8 24 plus 6 30 plus 4 34 plus 2 36 by 36, that is 1. So this is the probability distribution of x. We can write it like this: the probability distribution of x is P0 is 1 by 6, P1 is equal to 5 by 18, P2 is equal to 2 by 9, P3 is equal to 1 by 6, P4 is equal to 1 by 9, and P5 is equal to 1 by 18. This is the complete probability distribution of the random variable, which is described as the absolute difference on the upper two faces observed when two fair dice are rolled. Suppose I want to calculate the expectation here. So that is becoming 0 into 1 by 6 plus 1 into 5 by 18 plus 2 into 2 by 9 plus 3 into 1 by 6 plus 4 into 1 by 9 plus 5 into 1 by 18. So one can simplify this, it is 35 by 18. You can see that actually it is slightly less than 2. If we calculate expectation of x square, then it is 0 square into 1 by 6 plus 1 square, so that second value, plus 2 square into 2 by 9 plus 3 square into 1 by 6 plus 4 square into 1 by 9 plus 5 square into 1 by 18. Once again you can simplify, it is equal to 35 by 6. So the variance of x is equal to expectation of x square minus expectation of x whole square, that is 35 by 6 minus 35 by 18 square. So this can be simplified. it is equal to 665 divided by 324, which is little more than 2. Let me give one more example of a discrete distribution. An urn contains n distinct marbles. Marbles are drawn successively with replacement from the urn at random until a marble is repeated. So, for example, we can put some tags on those marbles. So, one marble is drawn and its tag is noted. The marble is put back in the urn and then another marble is drawn. Now, it can be the previous one or it can be another one. If it is the previous one, we stop, otherwise we continue. So, then again we put it back and draw another one. So, again it can be one of the two previous one or it can be a new one. Like that we continue till we get something which is drawn before. So, let us consider x be the number, let x denote the number of draws needed to complete the experiment. So, we want to find out the distribution of x. So, x can take values 2, 3 and so on up to n plus 1. Since there are total n marbles which are distinct, therefore, certainly at the n plus first draw you will have repetition. After that there is no need, because if in all the trials you get a distinct one, then certainly on the n plus 1th trial you will get the one which has been drawn before. So, what is the probability that x is equal to 2? That means on the first draw whatever marble was drawn, it is drawn again. So, if we draw one and that tag is noted, then it is one of those n. So, in the second one if we are drawing that, the probability of that will be 1 by 1. So, we can write it, that is the marble drawn on the first draw is drawn again. What is the probability x equal to 3? That means in the second trial we got a distinct one. Now, in the first trial you draw one and we remember the tag. In the second one that is not drawn. That means whatever is drawn is from the remaining n minus 1. So, the probability of that is n minus 1 by n. Now, in 1 and 2 draws, two distinct marbles are there, and in the third one we draw one of that. So, the probability of that will be 2 by n. So, we can say that is the marble on second is distinct from the first and third is any of the first two. Let me repeat this argument here. X is equal to 2 means that whatever is drawn on the first is again drawn on the second. So, if we are considering some draw on the first one, then that is fixed out of n, 1 is fixed and we are drawing it again. So, the probability of that is 1 by n. In the second case, if x equal to 3, that means in the second draw we get something distinct from the first one. So, the probability of that will be n minus 1 by n, and then we get something which is from the first two. So, that is 2 by n. So, like that we can continue. Let me write first few terms. What is the probability x equal to 4? So, that will be first one is distinct, second one is distinct from the first one, the third one is distinct from the first two. So, n minus 2 by n, and then it is one of the first three. At the ith one, n minus 1 by n, n minus 2 by n, and so on, n minus I plus 2 by n, and I minus 1 by n, and so on. What is the probability x equal to n plus 1? That is n minus 1 by n, n minus 2 by n, and so on up to 1 by n, finally n by n. We can verify that sigma probability x is equal to I is equal to 2 to n plus 1 is 1. So, actually for checking that you have to use the backward summation. Start from the end and use term by term sum. Now, I have discussed in detail one particular kind of random variables. They are called discrete random variables. So, the discrete random variables are the ones which take finite or countably infinite number of values. In the probability theory, there are certain specific random variables which are used commonly, and they are nice to describe various physical situations. One of them is the famous binomial distribution. So, in your syllabus also in the class 12th, you are actually studying the binomial distribution. So, let me describe that. And this binomial distribution is named after Jacob Bernoulli, the Swiss mathematician, and his published book Ars Conjecturi is one of the most, you can say, popular books, and it is one of the fundamental books of the probability theory. Here he described some experiments which are dichotomous in nature. That means, in which the number of possible outcomes are 2. So, let us consider, for example, somebody falls sick and he goes to a doctor and gets the medicine. Then the outcome can be that he gets treated or he does not get treated from that medicine. That means, you are looking at 2 outcomes, getting treated or not getting treated. Somebody appears in a competitive exam, so he may get some marks, but we may be interested in knowing whether he qualifies the exam or he does not qualify the exam. A shooter hits at a target, so we are interested in knowing whether the outcome is a success, that means he successfully hits the target or he misses the target. So, likewise, there are large number of real life situations where the experiment may be complex, but we are interested only to look at 2 outcomes, because that may be of some interest for recording purpose. So, such experiments are called Bernoullian trials or Bernoullian experiments. In many real life experiments, one is interested in only two possible outcomes. For example, hitting a target. So, success or failure, two outcomes are there. Treating a patient, cured, not cured. Appearing in exam. So, you can say qualifying or not qualifying. So, in such experiments, we specify one outcome as success and another outcome as failure. So, let me write S for success and F for failure. Okay. These are called Bernoullian trials. So, let us make an assumption. Suppose n Bernoullian trials are performed under identical conditions and independently of each other. And suppose the probability of success is same in all trials, say P, and so probability of failure is also the same in all trials, say 1 minus P, that is Q we can write. Okay. So, here this P and Q will be numbers between 0 and 1. Okay. Let X denote the number of successes in n trials. Then X is a discrete random variable. What are the possible values of X? X is a discrete random variable and it can take values 0, 1, 2 and so on up to n. You are conducting the trial n times. So, you can have all the failures, 1 success, 2 success or all the success. So, the possible values of X can be 0, 1, 2 up to n. What is the probability of say X is equal to K? Now, you are having, let me just draw it here, these are the trials, okay, 1, 2, 3 and so on. So, now you are saying that out of n trials, K of them are success. The trials are conducted independently. In one trial, the probability of success is P. So, if you consider K success, the probability becomes P into P up to K times, that becomes p to the power k. But it also means that remaining n minus k trials, they result in failures. Now, the probability of one failure is 1 minus p or q, and again the trials are independent. So, it becomes q into q n minus k times. So, it becomes q to the power n minus k. We are calculating what is the probability that out of n Bernoullian trials, there are k success and n minus k failures consequently. So, now there are total n trials. Now, these k values which are resulting as success can be any of these k. So, the number of ways of choosing that will be n c k. So, k is equal to 0, 1, 2, n. So, you are describing, let me call it pk. So, p0, p1 up to pn, you have allocated the probabilities corresponding to all the possible values of the random variable x. This is called binomial distribution. Also, it is called Bernoulli distribution. So, binomial distribution name is evident because you are using the binomial coefficients here. First of all, I will try to demonstrate that it is a valid assignment of the probabilities. We first show that this is a valid probability distribution. That is sigma pk, k equal to 0 to n, this must be 1. So, let us look at this. This is n c k p to the power k, q to the power n minus k, k equal to 0 to n. So, that is equal to, if I write all the terms, it is n c 0 q to the power n plus n c 1 p q to the power n minus 1 plus n c 2 p square q to the power n minus 2 and so on, plus n c n p to the power n. If you remember your binomial theorem, then from the binomial theorem, this is nothing but the expansion of q plus p to the power n. Now, q is 1 minus p, so q plus p is 1. So, it is 1 to the power n, that is equal to 1. So, sum of all the probabilities is 1 and all the probabilities are non-negative. Therefore, this is a valid assignment of the probabilities. I have already introduced the concept of expected value or the mean and the variance. So, let us see for the case of binomial distribution what are these values. Okay. So, expectation x, that is the mu, that is equal to, by the definition, it is the value multiplied by the probability, that is k into pk, k equal to 0 to n. Now, this is n c k p to the power k q to the power n minus k, k equal to 0 to n. You can see that in the summation here, the first term is corresponding to k equal to 0. So, when you put k equal to 0, this term is actually 0. So, we can actually say it is equal to k equal to 1 to n, k into n c k p to the power k q to the power n minus k. In order to evaluate this, we need to expand this permutation combination notation. So, that is equal to summation k equal to 1 to n k n factorial divided by k factorial n minus k factorial p to the power k q to the power n minus k. When we use this notation, we assume that this factorial notation. So, factorial 1 is 1, factorial 2 is 1 into 2 and so on, and we also make assumption that k for 0. So, 0 factorial we take trivially to be 1 as a convention, so that with this notation remains valid. So, we can write it as n factorial divided by k minus 1 factorial, and this term I write as n minus 1 minus k minus 1. So, this numerator I write as n factorial p to the power k q to the power n minus k equal to 1 to n. So, here I will make some change in the notation. Let us put k minus 1 is equal to m. Then this becomes m is equal to 0 to n minus 1. This n I can take out. So, you will get n minus 1 factorial p to the power k minus 1 q to the power n minus 1 minus m divided by m factorial n minus 1 minus m factorial. This p I have taken out. So, what I did here, let us compare these two terms. In this term I wrote n factorial as n into n minus 1 factorial, and this 1 n I have taken outside. Similarly, this p to the power k minus 1 I have written as p to the power k minus 1 and 1 p I take outside. Now, this term is q to the power n minus 1 minus k minus 1. So, k minus 1 I am writing as m. So, this becomes n minus 1 minus m. So, this term then becomes np sigma m is equal to 0 to n minus 1, n minus 1 choose m, p to the power k minus that is becoming p to the power m now, q to the power n minus 1 minus m. So, this becomes np, and now this term if you see, it is nothing but the expansion of q plus p to the power n minus 1, now which is 1. So, it is np. So, what we have proved that the mean of the binomial distribution is np. Let us try to physically interpret it. In one throw of a coin, or you can say in one trial of the Bernoullian experiment, the probability of success is p. X denotes the number of successes. So, what is the average number of success or expected number of success? That is n into p, which is natural to think, because if p is the proportion, then np denotes the out of total how many are coming. Let us look at variance of this distribution. Now, for variance we have used the formula expectation of x square minus expectation of x whole square. Now, to calculate expectation of x square, we further resolve it by writing it as, the reason is that if you look at the expression for expectation x, the simplification is done by cancelling out one of the factorial terms. So, if I have a square term, then that cannot be cancelled. So, that is why it is better to consider it in this particular fashion. So, that is equal to expectation of x into x minus 1 plus expectation of x. Expectation x has already been calculated, it is np. So, now I calculate expectation of x into x minus 1. K into k minus 1 n c k p to the power k q to the power n minus k for k equal to 0 to n. You note here that corresponding to k equal to 0 and corresponding to k is equal to 1, this term becomes 0. So, we can write this summation from k equal to 2 to n k into k minus 1, n choose k, p to the power k, q to the power n minus k. So, that is equal to k into k minus 1, k equal to 2 to n factorial divided by k factorial n minus k factorial, p to the power k, q to the power n minus k. In this one, I cancel out this k into k minus 1 from the first two terms of this k factorial, that is k into k minus 1 into k minus 2 factorial. So, I get the term n factorial divided by k minus 2 factorial n minus k factorial, p to the power k into q to the power n minus k. In order to resolve this, I consider the breakup like this. N factorial I write as n into n minus 1, and here I will get n minus 2 factorial divided by k minus 2 factorial, and this term can be written as n minus 2 minus k minus 2 factorial. This I write as p to the power k minus 2 and p square I write outside into q to the power n minus 2 minus k minus 2, k equal to 2 to n. Once again I define k minus 2 is equal to say m. Then this becomes n into n minus 1 p square sigma m is equal to 0 to n minus 2 n minus 2 factorial divided by m factorial n minus 2 minus m factorial, p to the power m, q to the power n minus 2 minus m. So, this is becoming n into n minus 1 into p square, and this is nothing but the expansion of q plus p to the power n minus 2, the binomial expansion. So, this q plus p is 1. So, this becomes n into n minus 1 p square. So, let us go back to the expression here. Expectation x square was expectation x into x minus 1 plus expectation x. So, we get expectation of x square as n into n minus 1 p square plus np. So, variance of x, that is equal to expectation of x square minus expectation of x whole square, that is equal to n into n minus 1 p square plus np minus n square p square. So, we can do little bit of simplification here. The first term here is n square p square, and here it is minus n square p square. So, that cancels out. So, you get np minus np square, that is equal to np into 1 minus p, or you can say npq. So, interestingly, now we have calculated expectation of x as np and the variance of x as npq, where x has a binomial distribution. Something you can note here, q is a number between 0 and 1. So, npq will always be less than np. So, you can actually make a statement here as q is between 0 and 1, npq is less than np. So, in a binomial distribution, the mean is always more than the variance. We can also write down the expression for the standard deviation. that is square root of NPQ. Now we can also look at the special case when P is equal to half. That means when the success and failure probabilities are same, then what are the expressions? When the success and failure probabilities are the same, that is P is equal to Q is equal to half, then the distribution takes a very simple form, that is probability x is equal to k, that is equal to nck half to the power n for k equal to 0, 1 to n. In this case, if you look at the plotting here, if I consider probability x is equal to say n minus k, then that will be ncn minus k half to the power n, that is nck half to the power n, that is probability x equal to k. So, when the success and failure probabilities are same, then the distribution allocates equal probabilities at the points which are symmetric. That means, if I consider 0 and n, then the probability will be same. If I consider 1 and n minus 1, then the probability will be same. So, let me just write it. So, for example, P0 is equal to Pn, that will become simply 1 by 2 to the power n. If I consider P1 and Pn minus 1, then that will become n divided by 2 to the power n. Similarly, you can consider other values. So, this is one special case when the success and failure probabilities are same, and in this case expectation of x becomes n by 2 and variance of x becomes n by 4, and the standard deviation becomes square root n by 2. In the next class, I will consider various applications of the discrete distributions. So, that means including the evaluation of expectations, variance, how to calculate various probabilities related to binomial distribution and some other discrete distributions. So, I will spend sufficient time about the problems on these distributions.